right? Pressure equals W times H. W is the weight density, and H represents the height or depth, right? So it could be going up or going down, but if we're talking about a fluid, I can't physically conceive of a situation here, like based on materials that I have available to me, where I would be submerging. I don't know what's the opposite of submerging, like, but I would want to be submerging, but in an upward direction. Upward direction. What's that? Merging? Like anti-submerging? I don't know. I'm sure there's a name for it, but it wouldn't make sense to be going upwards. But height and depth usually go hand in hand. Depth meaning the negative quantity for height, so we still use the H. And also we try to stay away from using D to represent too much of anything, because we're generally, when we're integrating, going to have a D built into it, dx, dy, and it leads to a source of confusion if we have a D representing other things. All right. So basically, what this is telling us is if we know the weight density of a liquid per unit of volume and the depth in which we're submerging the object, then we'll be able to determine the fluid pressure. All right. Now, fluid force is that fluid pressure multiplied by area. All right. So I'll read it anyway. Pascal's principle states that the pressure exerted by a fluid at depth h is transmitted equally in all directions. Because fluid pressure is given in force per unit area, P equals F over A. A fluid force on an object at a given depth would be the pressure times the area of the object. All right, so what that means for us is that we're taking the P, which we know is WH from up here, and multiplying it by A. So we're expanding out and getting a new formula. The issue is, and it's a meaningful issue, there's lots of ways in which you could submerge an object. First off, we're going to make the assumption that the object is flat in some regard. Right? It might have a different geometric shape, it might be rectangular, circular, or whatever, but it's going to be flat, a flat surface. Right? So that's one thing. The other thing ends up being, how is it submerged? I mean, I don't know if you've ever tried submerging one of those boogie boards. Like you go into a pool and you try pushing it down, and then you found out the hard way what happens when you let go. It's somewhat painful. Well, it has varying degrees of painfulness depending on where you get struck. So, yeah, I can't elaborate, but so there's that. But then if you took that same boogie board and submerged it vertically, it's easier to push down, still as dangerous. Because now you're looking, yeah, come on. So, but it's easier to push down. Obviously, the point or the moral of the story here is that there's definitely different force acting on the object depending on how you are submerging this object. All right, so we'll start with the horizontally oriented one. All right, so if it's submerged horizontally in 6 feet of water, that means that at that particular depth, I used to watch submarine movies all the time, over and over and over again, like Hunt for Red October, Crimson Tide, K-19, The Widowmaker. That one sucked, but I watched it. It was, U-571, Matthew McConaughey, right? Yeah, that was a good one. They're coming out with a new one. I forgot. I saw the ad for it last night. It looked like this generation's version of Hunt for Red October. I don't know how I feel about it, but I'll probably see it anyway. Anyway, the reason I bring that up is because you can't watch a submarine movie without at some point them losing propulsion and slowly sinking to the bottom of the ocean. And then somebody with a countdown of like 5 minutes to hold crush depth. 2 minutes, and it's like, all right, okay, get it. You know, can we kind of speed this along to the part where the engineer miraculously fixes the engine and you get back to the service? You know, it's going to happen, and not to end the movie 20 minutes in with a crushed submarine. If they were going to do that, they would have done it in the opening scene, and then it'd be like, oh, just kidding, it's not really about that boat, it's about the boat that's going to avenge the loss of that boat. You know? So anyway, different depths have different amounts of pressure associated with them. If you're at a singular depth and all of your body or whatever the thing that you're submerging is at the same depth, it's being acted on in the same way by the pressures that are at that depth. Long story short, it's really easy to figure it out if it's a horizontally submerged object because it's consistently at the same depth. In this case, 6 feet of water. All right, so the fluid force, F, would be the weight density, 62.4, multiplied by the depth, multiplied by the area of the object. Because again, that force is being transmitted to all parts, all components of the area of that submerged figure. So 12 square feet. And then we do some math. And we get an answer. And you say, can you please put this on the test? Yeah, but then we have to talk about the vertically oriented submerged figure. 4492.8 less 4492.8. All right, so in terms of units, pounds per square feet make up the weight density. So I'm just going to carry my calculations down below. Pounds per square feet multiplied by the depth, which is in feet, multiplied by the area, which we knew was in square feet. Simplify all this, and you get pounds times feet, also known as foot-pounds. But I'm fine with pounds times feet, just the other way. But we do need to have the appropriate units. Most of the units in a science class that you may have taken, they come from calculus processes. So when you're looking at newtons and joules and things like that, they come from the differentiation process and then just a collection of the appropriate units related to that process. In this case, it was simple multiplication, so it wasn't that bad. But if you were ever wondering, if you were sitting in a science class, be like, foot-pounds, that sounds weird. Where did that come from? Here's the origin story. No, that's just a notation. It's foot-pounds now. Yeah, that's just how they write it. It's a weird thing to think about, but that's science people taking liberty.